Alright, so our final video for chapter 3 is going to take a look at forming some ions for transition metals. We're also going to be discussing ionization energy and some of the general trends once we take a look at these transition metal ions. So when we take a look at forming transition metals, normally we'll see that using an example like vanadium, we'll see vanadium as a general rule for its electron configuration has an argon core with a 4s2 3d3 configuration. And as we start to take a look then at some of the common ions that vanadium makes, one of the common ions we'll see inside the transition metals is a vanadium 2+ compound. However, when we take a look at these, we're not always going to go in the same filling order, and this is because when we take a look at our configuration, we'll see that this becomes a 4s0 3d3 assignment. So in this case, when we took a look at some of our transition metals, we generally removed the s electrons first. And so this is for a few reasons that we talked about earlier. If you'll recall, when we took a look at assigning where the d orbitals are relative to the s orbitals, we'll sometimes say that the d orbitals can be considered part of the core electrons, especially when we start to occupy those. We've also seen instances where having electron-electron pairing, we've been able to see our setup. But in this case, our 4s and our 3d orbitals are very close in energy. And because of this, and because of how close they are, sometimes we'll see even small amounts of electrons can alter those chemical reactions. So when we do our setup, we have, this means that when I take a look at that 4s2 and that 3d3 configuration, we're going to see in fact that since these are so close in energy, that this electron-electron repulsion just like we saw with nitrogen and oxygen, will bump that orbital's energy up. And so this 4s will actually become the highest energy orbital. And so what that means is we'll see some states of vanadium are going to be, in this case a 2+ state, would be missing the 2 valence electrons. If we took a look at a vanadium in the 5+ state, we'll see that we have that same argon core, but now we've stripped away those 3d electrons as well. So we'll see that this is a 4s0 3d0 when we take a look at those ions. So in this case, what this means for us is when we take a look at the periodic table, we're going to have some variable charges with our metal ions. For example, when we take a look at chromium, chromium's electron configuration, since it falls in the one spot next to vanadium, we'll see chromium has a 4s1 3d5 configuration. And because of this separate pairing and how the d electrons fill up, we're going to observe that chromium can form a whole bunch of different charges with these different electron configurations. And this is going to have to do with a little bit more stuff that we get into Chem 2. But we'll see that chromium can exist in a chromium 2+. We'll also see that chromium can exist in a chromium 6+. So in this case, what this means is that my electron configuration would start taking the s electrons first. So in this case, I would see that my chromium would actually be an argon core with a 3d4 configuration for my chromium 2+ ion. So again, be aware as a general rule, for our transition metal ions, we will take away the s electrons first. And why is this? Why is it that the s electrons end up coming out first? Do we have data that supports this? And the answer is yes. The way that we know this trend exists is because of a concept called magnetism. And there are two different types of magnetism. We can either classify a compound as paramagnetic or diamagnetic. If a compound is paramagnetic, that means that there are unpaired electrons in the electron configuration. And as a result, we'll see that this exhibits a stronger magnetic field. So that means it'll interact with a magnet. A diamagnetic species, on the other hand, generally won't interact with a magnet. And that's because these diamagnetics only have paired electrons. In their electron configuration. And generally, these are a very small or an unnoticeable magnetic field. And as a result, they won't interact. So, for example, when we take a look at, say, silver, we'll see that silver has an electron configuration that has an argon core. Excuse me, silver has a krypton core. I was one off. We have that krypton core, but we'll then observe that our electron configuration is a 5s1 4d10. And this is supported by the fact that silver is considered paramagnetic. In this case, the atom is paramagnetic. And that's because there's that unpaired electron in the 5s orbital. But when we take a look at silver as an ion, we'll see that silver as an ion only has that 4d10 configuration, and it becomes diamagnetic. And it's because of this that we're able to then support our claim with our fact that the 5s orbital gets pulled before the 410. In the event that silver had a 5s249, we would see that the configuration would be different. We'd go from a 5s249. That would mean that as an element, silver would be paramagnetic. And if we took away the d electron like we thought, 4s248, this would still be paramagnetic. And that's because when we take a look at this, if I have my 5s2, I would see that I have 1, 2, 3, 4, 5, 6, 7, 8. I still have 2 unpaired electrons. But this is not what I observe experimentally. I observe that silver as a metal is paramagnetic and silver as an ion is diamagnetic. And so we're able to use these observations of magnetism then to justify why we are indeed pulling the s electrons instead of the d electrons first. So then let's take a look at what's a little bit more experimental data. In this case, we're looking at what's called the ionization energy. And ionization energy is the amount of energy needed to remove one valence electron from an atom in the gas phase? So let's take a look at this data and see what we come up with. We can do this by a technique called X-ray photoelectron spectroscopy. Excuse me. And what we'll do is you'll notice that our first ionization energies, the noble gases, are the highest values of each period. And this makes sense because if you think about it, we're going to have the valence electrons on helium, neon, argon, and the noble gases. These will have the highest effective nuclear charge in the family. Conversely, we'll observe the same phenomenon when we take a look at the alkali metals. The alkali metals that start off our series. And this is because the valence electrons have the lowest effective nuclear charge. They have the lowest pull, keeping those electrons attached. Now you'll notice there are a couple interesting exceptions. Whenever we start to occupy the p orbitals, or whenever we start to have paired electrons, we'll see that, so like in the p orbital set, for example, we'll see that boron and, let's see, boron, carbon, nitrogen, oxygen will then have a little bit of a dip. And why is this? Well, when we take a look at the electron configuration, we know that we'll use nitrogen and oxygen, for example. When we take a look at oxygen and nitrogen, we'll see that nitrogen had that configuration of our 2p3, whereas oxygen has a configuration of 2p4. This is where we start to see that paired electron come into play. And so in this case, with that paired electron, that means that there's a little bit of electron-electron repulsion again. And so we'll see, because of these little dips here, is where we start to see that electron-electron repulsion come into play. And that's what causes our dip in the ionization energy. I need less energy, so it makes it easier to remove that valence electron. And then when we take a look at the difference between beryllium and boron, this is when we go from a 1s2 to a 2s2 configuration to a 2s2 2p1 configuration. And what this means, since we're adding the 2p1, this means that my electron's getting farther away from the nucleus, feeling less charge. There's more screening because of that, those 2s2 electrons, and it's easier to take that one away. So then let's take a look at one more interesting trend inside of the period 4 transition elements. I'm going to blow this up a little bit. So we'll do the same thing that we did last time. We're going to label some of these elements here so we can pinpoint which one's which. We've got potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Okay, so as we go through, we'll notice that when we dip from titanium to vanadium, we'll see that it becomes a little bit easier. Same thing with chromium. It starts to become a little bit easier to take a valence electron away. Same thing, we'll see that there's a little bit of a bump up. It becomes harder with manganese, and it starts to decrease again as we work towards nickel, and we start to increase again at copper and zinc. The expansions in copper and zinc can then be explained because we go from like mainly a D configuration up to a 3D 4s1 3d10, 4s2 3d10, and we'll see that these electrons have a larger nuclear charge, which is why it gets kind of trickier. But why is it that vanadium gets easier, and why is it that iron gets easier than some of these other ones? And it's because that's when we start to observe like that 4s2, 3d3. But in particular, the big thing I want you to focus on is this spot right here. The reason that it starts to get easier with iron is because then we start seeing this trend where it becomes my manganese configuration has that ending of a 4s2 3d5. But when we look at iron, we go from 4s2 to 3d6. And this means that we have that electron-electron repulsion again. That makes it a little bit easier to take that out. So in this case, electron-electron repulsion can be used for almost every single explanation of why we see a dip when a general trend says that my ionization energy increases as I go left to right on the periodic table, and why my ionization energy decreases as I move from top to bottom. So again, our general trend, as you move up and right on the periodic table, we'll see ionization energy increases. And in this case, we're talking about the first ionization energy. And as you start to think about the second, third, fourth ionization energies, just adjust those to account for what the new electron configuration looks like. For example, if we take a look at the second ionization energy, we'll see that sodium has a way higher second ionization energy than magnesium does. And this is because the sodium ion is already at its noble gas configuration, whereas the magnesium ion still has one valence electron. So you'll start to see just that you need to adjust how you think about the second and third and fourth and additional successive ionization energies. And so lastly, what we're going to do is we're going to finish off with a small table here. And what this does is this summarizes some of the key things we've already talked about, as well as two additional characters. Metallic character, that one's pretty straightforward. How metal-like is it? But in this case, electron affinity means how likely we are to accept electrons. So kind of as we move from, we'll see that it decreases as I move across a row. It becomes more negative, more likely. Remember, a lower number or more negative means that the electron affinity gets stronger. And so we see that atoms, as we move across the row, are more likely to accept electrons because, again, that effective nuclear charge will increase as we move left to right. So this should wrap up our discussions then on chapter 3. And in this chapter, we summarize kind of what electrons looks like, how that affects how that'll affect the structure of the periodic table, and how there's a correlation between those two, as well as some trends that we can use the periodic table to help us predict.